Let me show you how to be a good breezy and change your predictions.
In this episode, we dive deep into gravitational wave astronomy with Christopher Berry and John Veitch, two senior lecturers at the University of Glasgow and experts from the LIGO-VIRGO collaboration. They explain the significance of detecting gravitational waves, which are essential for understanding black holes and neutron stars collisions. This research not only sheds light on these distant events, but also helps us grasp the fundamental workings of the universe. Our discussion focuses on the integral role of Bayesian statistics, detailing how they use nested sampling for extracting crucial information from the subtle signals of gravitational waves. This approach is vital for parameter estimation and understanding the distribution of cosmic sources through population inferences. Concluding the episode, Christopher and John highlight the latest advancements in black hole astrophysics and tests of general relativity, and touch upon the exciting prospects and challenges of the upcoming space-based LISA mission. So, strap on for episode 101 of Learning Bayesian Statistics, recorded February 14, 2024.
Let me show you how to be a good breezy and change your predictions.
Hello, my dear Bayesians! Today, I want to thank Giulio for joining the Good Bayesian tier of the show's Patreon. Giulio, your support is invaluable and literally makes this show possible. I really hope that you will enjoy the exclusive sticker coming your way very soon. Make sure to post a picture in the Slack channel. And now, on to the show.
Had to be a good breezy and change your predictions.
Christopher Berry, John Veitch, welcome to Learning Bayesian Statistics.
Thank you very much for having us.
Yes, thank you a lot for taking the time, even more time than listeners suspect, but we're not gonna expand on that. But yeah, I'm super happy to have you on the show, and we're gonna talk about a lot of things: physics, of course, astrophysics, black holes, and so on. But first, how would you both define the work you're doing nowadays, and how did you end up working on this?
I can go first. I guess I'm slightly older than Christopher, but I started doing gravitational waves when I was a physics student at Glasgow, and I got involved with the LIGO, actually the GEO experiment first of all, which is the gravitational wave detector in Germany.
Mm-hmm.
Its bigger brother is the LIGO and the Virgo detectors that we're going to talk about more today. And ever since then, I thought the project was fantastic. I'll tell you all about the kind of cool science that it does, but I just wanted to get involved in the discoveries of gravitational waves and what they can tell us about black holes and so on.
Yeah, so I got involved back in my PhD. My PhD was largely about gravitational waves we could maybe detect in the future with an upcoming space-based mission called LISA, due for launch in the 2030s. And I remember my advisor telling me, I hope you're okay, there's not going to be any real data. And I was like, yes, that's great. I just want to play around with the theory stuff. And then I guess fate conspired against me. After my PhD, I moved to the University of Birmingham. That's where I first started working with John. We were at the University of Birmingham together. And I got involved in LIGO-VIRGO data analysis. And we happened to make our first detection just a couple of years after I joined in 2015. And we've been very busy since then analysing all the signals, figuring out the astrophysics of them. So each individual source, and then putting them together to understand the population underneath. So now, we're both at the University of Glasgow working on analysing these gravitational wave signals and understanding what they can teach us about the universe.
Yeah. So as listener can already tell, I guess, fascinating topics, lots of things to talk about and dive into. But maybe to give us like a preview of things we're gonna talk about a bit more. You guys are using some Bayesian stats, right, in these analysis. Am I right?
Yeah.
Yeah,
So I think, we look at, I guess, two levels of Bayesian stats. So the first is what we refer to as parameter estimation. So given a single signal, trying to figure out what are the properties of the source. So the signals we most often see are, say, two black holes spiraling in together. So we look at the patterns of gravitational waves that it emits, and from this we can match templates and then infer these are the masses of the two black holes, this is the orientation of binary, the distance to the binary, and parameters like that. So we use Bayesian stats and the sampling algorithms like nested sampling to map out a posterior probability distribution. And then I guess the second level of this, we do what we call a population inference, so a hierarchical inference of given an ensemble of different detections, correcting for our selection effects that we can detect some signals easier than others. What is the underlying astrophysical distribution? So what is the distribution of masses of black holes out there in the universe?
Yeah, so fascinating things. And John, you want to maybe add something to that? Just as a teaser, we're going to dive a bit later in the episode into what you guys actually do. So as Christopher just said, nested sampling, population inferences, but anything you want to add as a teaser for listeners?
I would add something about the background of how it works within the LIGO scientific collaboration. So when I started doing my PhD, my advisor, Graham Moen, taught me about Bayesian statistics, Bayesian inference, and I never learned it as an undergraduate at all. It just blew my mind. Like, here we have this mathematical theory of learning. Why aren't we using this everywhere? And in those days, it really wasn't being used very much in LIGO, because a lot of the people that started the collaboration were coming from particle physics background, and they're very frequentists. You know, they're counting and cutting all of their events to try and measure the, discovery of the Higgs boson or whatever. So it was kind of novel in gravitational waves back then, but since then, as Christopher said, it's been applied all over the place to all kinds of different problems. So it's been quite exciting to watch that happen over the years.
Yeah, I remember when we had our first detection, and we were writing up our results. And I think at that time, still a lot of the collaboration was very frequentist. So we were writing in our papers, we have a posterior probability distribution for the masses. And there were people going, hey, what's that? What's a posterior? We've never come across this before. Can you explain it to us? And now it is very much accepted. And yeah, everyone has a new detection about where are the masses? I want to see this probability distribution. Where is it?
Yeah. And what do you think drove that evolution and that change?
I think Bayesian stats is very popular in other parts of astronomy. So in a sense, it was kind of inevitable that it would make its way over to gravitational wave astronomy. It's only a matter of time. But I think, the problems that we were trying to solve, particularly for the parameter estimation type analysis, did lend itself to a Bayesian analysis, because you have a unique event. We only see a very small number of gravitational waves. We see all the time, but it's still measurable in the dozens, not the millions. So we have to make the most out of every single one. And the signal to noise ratio is rather low. So having a grasp on the uncertainty is also very important if you want to do science with it.
Yeah, that makes sense. And so it was mainly driven by just Bayesian stats answering a need in what you wanted to do, basically, which is also which is something I often see in fields where psychology, from what I've seen in the last few years, for instance, psychometrics, things like that, have seen a big rise in Bayesian statistics because they have been able to answer the questions that researchers had and that they could not answer with the tools they had before. So basically a very, very practical, oriented view of things. And then afterwards, let's say the more epistemological, philosophical side of things enters to also justify that. But most of the time, it's a very practical, driven mindset, which is great, right? Because in the end, what you why you care about that. It's just like, is that the right tool to answer the questions I have right now? And yeah, for what it's worth. Yeah, go ahead, John.
I think the pragmatism is what puts food on the table at the end of the day, but during my PhD, I was trying to look for not the kind of black hole binaries that we'll be talking about later, but for monochromatic waves. So you imagine doing a Fourier transform of some data, and you have a single spike, and it has a bit of modulation on it. But really, there's no information about that spike in any area of the parameter space outside of the spike. So I learned about Bayesian statistics and tried to do MCMC on this problem, which was kind of like the most pathological problem that you could try and do MCMC on. That basically reduced itself to doing an exhaustive search of the parameter space. So I was kind of convinced by the epistemology originally rather than the piece, and it was only later that we moved to the more practical useful, I would say.
Yeah. No, that makes sense. And as you were saying, also that Bayesian stats is popular in other parts, of physics. That's definitely true in a sense that, for instance, in the car developers of PyMC, of Stan, you have a lot of physicists, often coming from statistical physics, and historically even the algorithms that we even use, MCMC algorithms, have been developed mainly by physicists or for physics purposes. So there is really this intrication here, almost historically, and that made me think that if listeners are interested, there is an interesting package that's called Exoplanet, and that's basically a toolkit for probabilistic modeling of time series data in astronomy, but with a focus on observations of exoplanets. So that's different from what you guys do, but that's using PyMC as a backend, so that's why I know it. And that's mainly developed by Dan Furman Mackey, if I remember correctly. I will put that in the show notes for people who are interested, because that is definitely something to check out if you are doing that kind of models. And that made me think that I didn't even thank our matchmaker, because today is February 14, but actually this episode was made possible thanks to a matchmaker, a Cupid, if you want, of Bayesian statistics, Johnny Highland. Thanks a lot for putting me in contact with Christopher and John. Johnny is a faithful listener, and I am very grateful for that, and for putting me in contact with today's guests. And so you mentioned already, Christopher, that you two work on the LIGO-VIRGO collaboration. Maybe, tell us a bit more about that collaboration, what that is about, and what the goal is, so that listeners have a clear background, and then we'll dive into the details.
So yes, LIGO-VIRGO Carrera is a collaboration of collaborations. So each of LIGO, Virgo, and Carrera operate their own gravitational wave detectors. So these are remarkable experimental achievements. We're talking devices that can measure distortions in space and time is what we're looking for. So in effect, what we do is we time how long it takes a laser to bounce up and down between some mirrors in one direction compared to another. We're looking for a part of less than 1 part in 10 to the 21. So it's equivalent to measuring the distance between the Earth and the Sun to the diameter of a hydrogen atom, or the distance from here to Alpha Centauri to the width of a human hair. So over many decades, experimentalists have developed the techniques to build these detectors, to design them. And we're now in a very fortunate situation that we have multiple of these detectors operating across the world. So we have 2 LIGO detectors in the US, one in Livingston, Louisiana, one in Washington, in Hanford. And we've got Virgo in Italy, just outside Pisa, Carrera underground in Japan, and in the coming decade, another LIGO to be built in India. And each of these observatories is looking for gravitational wave signals. The ideal source for gravitational waves would be a binary of 2 black holes or 2 neutron stars, very dense objects coming together, merging very quickly, very strong gravity, very dynamical objects. And we can detect these gravitational waves, and with those do astronomy. So instead of using a telescope to make observations with light, we're using these gravitational wave detectors to look for gravitational waves and uncover the astrophysics of these sources.
Yeah, thanks. So that's a very clear explanation. It's a bit like being able to hear the universe itself only looking at it, right? So that's another way of getting information about the universe, and that maybe allows us to also answer questions that we had, but we were not able to answer only with the telescope data. Is that the case, or is that mainly information that's parallel and similar?
Yes. So, go ahead.
Yeah, John.
Yeah, I think that's one of the most exciting things about it is it's completely separate from the electromagnetic spectrum. It's using the structural squeezing of space itself by these black holes and neutron stars. The waves that are given off are kind of an audio frequency. So, as you said, the detectors are picking up essentially the equivalent of sound waves, bulk motion of material rather than the jiggling of atoms. We're talking about the jiggling of whole stars and the movement of them in their orbits. And because you're looking at the bulk motion rather than the surface of the object, you can see right into the heart of what's going on in some of these very violent events. In principle, we should be able to see also inside supernovae if there are enough motion of material during the core collapse. That would also give off gravitational waves that we could see, although they are thought to be much weaker than those that we're looking at the moment of binaries.
I see.
One thing that's particularly nice we can do as well is really test how gravity behaves in very extreme environments. So, John, I don't know if you want to mention something about looking at the ring down of black holes.
Sure. I mean, as Christopher says, there's a very detailed prediction for how two stars should approach each other in their spiral over time. And the equations are horrendously complicated. You're talking about the full theory of general relativity. But once they've collided and they form a larger black hole, suddenly everything becomes rather simple and it acts just like a wine glass that's been excited with a fork, and then it gradually decays down and settles into its final state. Now, for a black hole, that happens extremely fast because they want to settle down as quickly as they possibly can, if you like. So the notes that they give off are milliseconds long rather than seconds long. But the frequencies and the damping times of those notes are measurable with gravitational waves. And by looking at them and comparing them to each other, we can check to see that the predictions of the theory are indeed what we would see in the world. So far, they do seem to be in agreement.
Yeah, and how can we even, like, something I'm wondering is that these collisions that you're talking about, they are happening millions of light years away. How are we even able to study them and also maybe tell us what we already have learned from them?
They're really quite rare events, the types of collisions that we're seeing. I mean, this is why they're millions, hundreds of millions, or even billions of light years away, is because they're so rare in the universe that we need to look out a very long way before we see one often enough to make the detections of them. So I mean, they do happen in local galaxies as well. There's no reason to think they wouldn't, but it's just they're so rare. I haven't seen one from a nearby source yet.
Yeah, so
they are remarkably energetic. So the amount of energy that is output as gravitational waves when you've got, say, two black holes coming together is phenomenal. For just that moment as they smash in together, more energy. So the luminosity, the amount of energy per unit time emitted right at that peak is higher in gravitational waves than if you were to add up all the visible light from all the stars that you could see in the universe. So it's a phenomenal amount of energy just over a very short way. So we just need to be listening to the universe to see these, to discover these sources and find out what they're trying to tell us.
The energy flux from these black hole collisions, despite the fact that they're hundreds of millions of light years away, is actually comparable to the flux from the full moon. So the brightest object in the night sky is surpassed by gravitational wave signals, except we can't see the gravitational waves because they don't interact very strongly with matter. And it's only by building these incredibly sensitive detectors to pick up their effect on distances that we can measure them.
Yeah, that's just it's fascinating to me that we're even able to like hear these waves in a way. So
I mean, just to hammer the point home, there's so much energy that they're carrying away, but the effect is so tiny, as Chris said, 10 to the minus 21 or less.
Yeah.
If you think about how those two things can be true at once, it's telling you that it takes an enormous amount of energy to produce a tiny distortion in space. So it's very, very difficult to warp space. And that's the consequence of general relativity.
Yeah. And then, so I think now it's a good time for you to tell us. So maybe Christopher, you can tell us that how do you use Bayesian stats to extract as much information as possible from these tiny wave signals? How is Bayes useful in this field, and how do you also actually do it? Are you able to use any widespread open source packages, or do you have to write everything yourself? How does that work concretely?
Yes, so for the type of sources we've been seeing, these binaries, we have predictions for what the signal should look like. So we have a template that is a function of their parameters, and we have a decent understanding of the properties of our noise. So the data is a combination of the signal plus some noise which you assume to be stationary over the short time scales that we're analyzing, and characterized such that the noise at individual frequencies is uncorrelated. So if you like, you get your data, transform it to the frequency domain, subtract out your template, you should be just left with noise, which is Gaussian at each frequency bin. And so you have a lot of Gaussian probabilities that you combine together. So that gives us our likelihood. You map that out, you change your parameters for your template, you evaluate that at another point in parameter space, map that out with your suitable prior, and you end up with your posterior probability for a single event. The number of parameters that we're typically dealing with is something like 15 for typical binary. Maybe that goes up to 17 when we add in a couple of extra ones, a few more if we're maybe looking at tests of general relativity. So it's enough that exploring the parameter space can't be just done by gridding it up and exploring it. We generally use some kind of stochastic sampling algorithm, but it's not one of these problems, at least yet, where we've got millions of parameters and it's a really high parameter space. In terms of the algorithms that we use to explore parameter space, we've got a long history of using MCMC and nested sampling for these. And I think John's really the expert on this. So, John, do you want to say some more about?
We'll get to that, yeah. Oh, you were done? Okay, perfect. So yeah, John, maybe if you can tell us, maybe let's start with nested sampling that you use a lot for your inferences. So can you talk about that, why that's useful, and also why you end up using that a lot in your work? Which problem does that solve?
So nested sampling is an alternative to MCMC. I don't know if your listeners will all have encountered it before. If you're a regular user of MCMC, though, it's definitely worth a look. It was invented in 2006, 2007 by John Skilling, who was a physicist. And the idea is that you're actually trying to evaluate the evidence, the normalization constant of the posterior, to allow you to do model selection in a Bayesian way. But as a byproduct, it can generate samples from the posterior as well. So this popped up around about the time that I was started a postdoc position at Birmingham, and we thought, well, why don't we give it a go and apply it to the problem of compact binaries. So at that point, there was no off-the-shelf package available to do this, and so we had to create our own and that was all coded up in C, of course, at the time. It wasn't such a big thing.
Yeah.
There was thousands of lines of code and all that. So,
Oh my god.
But yeah, so the reasons that you might prefer it over MCMC, people were trying to solve the same problem with parallel tempered MCMC. The compact binary parameter space has a fair amount of degeneracies, multimodality, and curvature in amongst those modes that make it a bit difficult to sample. The waveforms are very oscillatory and it's nonlinear problems, so it can be quite complicated. And getting a decent exploration of the prior was proving to be difficult for the MCMC, hence the need for parallel tempering. And nested sampling works a little bit differently because it starts off by sampling the whole prior in the first place. So you pick, say, 1,000 points, they're called live points, scatter them across the entire prior, and then compute the likelihood for every one of those. If you then eliminate the point that has the lowest likelihood and replace it with one that has higher likelihood than the lowest one, then you will still have 1,000 points, but they will all have a likelihood higher than the worst one. And you can see that, roughly speaking, the volume of that remaining set of points will be about 999 thousandths of the original one, just by random law of large numbers. And so if you repeat that process, always replacing a point, at the next iteration you'll have 999 thousandths of 999 thousandths of the original. And so eventually you'll shrink in a geometric fashion the volume that your points are contained within. And in doing so, you're walking uphill, you're moving towards the peak of the posterior. So unlike MCMC, it is guaranteed to terminate once you run out of hill to climb up, which was a nice feature. And it gives you the evidence for doing multi-selection. Once you've done the entire chain, you can resample those points from the chain and weight them according to the posterior to produce either independent samples or weighted posterior samples according to your needs. So it's a really effective algorithm. I like it because it's reliable. As I say, your run is guaranteed to finish. It might take a long time, but it will get there. There are, of course, places where it falls down. If you don't have enough live points, you can end up missing a mode. The challenge is really how do you explore that constrained prior distribution. And so over the years, there have been different approaches to doing that. The one that I started when I was coding it out from scratch was using MCMC inside nested sampling to just do a little MCMC chain to draw the next sample, which works fine, especially because we already knew how to do MCMCs for this problem quite well. But other people have invented the ellipsoidal bound multi-nest algorithm. Was one of the first very popular off-the-shelf solutions, and that was used also for gravitational waves. These days, there are more modern Python packages that do everything you need, either with MCMC or with ellipsoidal sampling or more complicated things like normalizing flows. A couple that I should mention at the moment for most of the gravitational wave work using Dynasty, which is dynamic nested sampling. Myself and the students who's now moved to Portsmouth have been NESI, which was a nested sampling with artificial intelligence that attempts to use some machine learning to accelerate this whole process.
Well, that sounds like fun. Yeah, I'm definitely gonna link to Dynasty, so the package you're using right now to do the nested sampling in the show notes. And if you have anything you can share on this new package you're working on, for sure, please add that to the show notes because listeners will be very interested. And maybe you wanna add a bit more about this project. So how would you use machine learning in this way to help you do the nesting sampling?
Yeah, I can say something about that. It's a cool idea. I mean, the enabling technology for this is a tool called the normalizing flow. And I don't know if you've talked about the podcast before, but they are a way of approximating complicated distributions using simple ones with a remapping of the coordinate system. So in our context, we were trying to make a good fit to the jump proposal for the nested sampler, if you like, because that has to evolve with the scale of the problem as the nested sampling proceeds. The more it shrinks, and it can shrink by a factor of 10 to the 20 over the course of the run. So you're going to need something adaptive to continue to have good efficiency. So we took this normalizing flow technique and applied it to this problem of fitting the existing samples, and then the advantage being that it allows you to draw independent samples, a bit like the ellipsoidal technique, but it doesn't require to have a fixed shape. So it's able to learn more complicated shapes for the distribution. Yeah, I'll pop the link in, and people are very welcome to give it a go.
Yeah, for sure.
Results with it.
Yeah. So folks, give it a go, try it. If you see issues, report them on the GitHub. Even better, if you can do a PR, I'm sure John will appreciate it. And actually, so that could not be better, because I will refer people to episode 98 of the podcast, where I talked with Marie-Lou Gabriel, who is one of the persons developing these kinds of methods, and we talked exactly about that. Adaptive MCMC augmented with normalizing flows, and we talked in the episode about how it offers a powerful approach, especially for sampling multimodal distributions, how it also scales the algorithm to higher dimensions, how you can handle discrete parameters, and how, like, all these ongoing challenges in the field. So if you're interested in the nitty-gritty details of what John just mentioned, I recommend listening to episode 98, because, well, Marie-Lou is really one of the persons developing all that stuff.
Sounds super interesting, Alex. I'm amazed at the power of some of these new techniques. Like, there's a revolution going on at the moment in this area, so it's a good time to be involved.
Yeah, no, for sure. So I will link to that, and also Colin Carroll, who is one of the PyMC developers, he also has a new package, working on a new package called Bayesian, and I know that they implemented this normalizing flow algorithm, and so now you can use that in PyMC directly through Bayesian, and to use that kind of algorithm and handle your multi-dimensional, multi-model distributions more easily. So I also link to that, because that's definitely super interesting if you have lots of weird distributions like that. And Christopher, to come back to you, you also mentioned that you guys do population inferences, and that's hierarchical models where you use a bunch of observations to infer the underlying distribution of the sources of the signal, if I understood correctly. So what does that look like? What do you guys do here?
Yeah, so we do the calculation in a couple of stages. That we always run the parameter estimation to get the events parameters for just one signal at a time first. And so the result of that is a set of posterior samples calculated with a fiducial prior. And what we want to do is then divide out that prior, put in a population model, see how well that fits. So calculate the evidence under the assumption of a particular set of hyperparameters, and then we have a inference one level up where we vary the population parameters, the hyperparameters for the population model, explore that to see what fits work. So that really is starting to get the astrophysics. So looking at the distribution of masses, are there more low mass black holes than high mass black holes? How does that scale? Is there little bumps in the distribution and things like that? It's next level up. The likelihood isn't quite as expensive as evaluating the waveforms, but we have some data handling issues of reading in all the posterior samples. And key to this is, as I alluded to, is correcting for the selection effects. So that we need to account for the fact that with our gravitational wave detectors, we can preferentially see some sources over other sources. So if you were just to look at the distribution of sources that we detect, you'll see, hey, there are lots of 30 solar mass black holes. There aren't too many 10 solar mass black holes. And if you didn't know about our selection effects, you'd naturally assume, okay, the universe is full of 30 solar mass black holes and 10 solar mass ones are much rarer. Whereas because our detectors are more sensitive to the high mass signals, those are intrinsically louder, so we can see them further away, we can see more of them. Once you correct for the selection effects, you actually see it's the other way around. There are many more, at least there should be many more 10 solar mass black holes than 30 solar mass black holes. And the fact we don't see so many 50 solar mass black holes, 90 solar mass black holes, tells you that the distribution does drop off quite rapidly. So this is a field that's growing quite nicely as we get more and more detections. Your uncertainties on the population basically go as the square root of the number of detections. What we're seeing a lot of work on is what does one assume for the population model. So when we started off, we're, I guess, following what is common in astronomy, we put a power law through for the masses. Just infer the power law index, basically, and the normalization for the overall rate, and see how that worked. Then we like, that's a bit simplistic. Let's add in a couple more parameters. Let's have, say, a little peak, a Gaussian add on top of that to get peak. Let's say have two power laws with the break, see how those fit. Let's put in another peak. And now people are looking at semi-parametric models. So, okay, what if we add a spline on top of that, see how we can vary that? Or what if we do something really flexible, so allow a bunch of kernels to come together and infer the population to get out of there. So a lot of the work at the moment is trying to see what is a good fit for the data, and then checking, is this overly complex? Are we overfitting? Is there a little bump there? Is that just because of a Poisson fluctuation that we've only seen so many events? So small number statistics means there's a few more here and a few fewer there, or is there actually some feature of the underlying population which may be a hint to how stars evolve? So I think it's quite an interesting time at the moment from this testing out models, trying to determine do they fit the observations quite well, and very excited for getting the results of our upcoming observing runs when we have a much larger number of detections and we'll really be able to constrain the models to higher accuracy and precision.
Yeah, so that's super interesting. And so here, to understand what you're doing, it's like you're hearing different sounds and you're trying to infer not really what the sound is about, but what is emitting that sound, what is the source of that sound.
Yeah.
And the issue is that these sounds can be emitted by a lot of entities, and a lot of these sources you don't really care about because, I don't know, they are on Earth, they are like, but what you're interested in are the sources outside, which are in space and which tell you something about the universe, which here would be mainly neutron stars and black holes colliding. How weird was that characterization?
Yes, that's good. I guess maybe a nice analogy might be, imagine you have a room full of people and you're trying to judge the composition of the room. And some of the people there, you have a bunch of librarians who are very quiet, and you have some, some heavy metal stars who are very, very loud. And so you've made your recording of the audio in the room, and then you need to try and reconstruct that. Okay, I can only hear one librarian. But given that the librarians are very quiet, there's probably a whole host of other librarians who I just missed because they're being too quiet. And I can hear lots of electric guitars going on, so I know there's some rock stars here. But I know they're very loud and they're easy. I probably will have detected 100% of those. So correct for those, that bias from the detection. We're very fortunate actually in gravitational wave detection that we can calculate our selection effects. It's quite easy for us to determine what sources we can detect and what we can't.
Okay.
This is a standing problem in astronomy, that you're we only have one universe, so we need to make sure we understand what we're seeing. And you can know what you detect, but it's very hard to know what you're not detecting. So a lot of astronomy is trying to correct for these. And if you have a telescope, that can be very difficult because you've got to calculate, okay, not just what did I see, but what could I have seen? So that would depend on where I was pointing the telescope. It would depend on the weather on a particular day and how cloudy it was. Whereas with our gravitational wave, it's much simpler. What we do is we can inject, is the terminology we use. We simulate signals, put those into our data, run our detection pipelines on that, and see what fraction of the signals that we injected would we recovered, and from that work out, as a function of source parameters, what was the probability that something was detected, and then use that in renormalizing our likelihood to establish, okay, how many of these sources should there have been, given that we saw this many.
Okay.
It helps a lot that gravitational waves are not blocked by anything in the universe that we know about, except for other black holes. But even then, other black holes tend to be very small. So when we are able to calculate exactly what the source is doing, it means that we've got a very good idea of what we will see. It doesn't really matter what's in the intervening space. The two veins of astronomy are dust and magnetic fields, and gravitational wave sources don't really care about either of those two things.
Yeah, okay, I see. And that's actually a good thing. Like that, indeed, that's quite a luxury to be able to compute your own selection bias. That's pretty amazing. Me, who've done a lot of political science, you usually cannot do that, so I'm very jealous. And can you tell us actually where does that noise come from? Because it seems like you're saying there is a lot of noise in your observations. Thankfully, you're able to tame that somewhat easily. Can you tell us a bit more about that? And John, it seems like you want to add something about that.
Most of the noise, in fact, all of the noise, is not of extraterrestrial origin. It's coming from the detectors and coming from the environment around the detectors. So in order to understand it, you have to know a little bit about how LIGO-VIRGO and Carrera work. So imagine a giant L shape, 4 kilometers long in the case of LIGO, with mirrors at the ends of the arms. And shining a laser into the coin, if you like, it gets split into two and sent down both arms, bounces off the mirror to the end, and then comes back and recombines. And if the arms are the same length, then the light will constructively interfere, or destructively, I may have that the wrong way around. But the point is, if the arms are different lengths, or if they're changing lengths, then the pattern of the light that comes out will change over time. So we are really worried about anything that can change that output of the laser in the detector. And so that could be due to the laser itself. All the lasers have some amount of noise in them. And so the lasers that are used in these detectors are some of the most stable lasers that you have. That have to be invented from scratch, basically, for this problem. It could be the thermal motion of the atoms in the mirrors. That's called thermal noise. We get around that by simply having a wide enough laser beam averaging over the whole surface of the mirror, cancelling out the mean motion to a low enough level to get it ready. But the laser also carries energy, and that energy pushes on the mirrors, called radiation pressure noise, which causes the mirrors to move a little bit. And think about the other way around, the laser energy is carried by photons, which are ultimately quantum objects. So they hit off the mirror discreetly, like raindrops on a roof. If you imagine, or if you're in a tent, you get the drops of rain. That's kind of what it's like. The lasers are enormously powerful. Still, they are made of individual photons. And so there's a shock noise associated with that, just due to the statistical fluctuation in the number of photons that arrive per second. Then we've got the environment as well, which is especially dominant at low frequencies. So we can't sense anything below about 10 hertz with these detectors that are above the ground because of seismic motion. Now, we do have a lot of techniques to try and screen the mirrors out from the motion of the Earth. They're hung on suspended optics, which act as a natural filter to prevent ground motion from propagating through to the mirror. But even so, we need to have active isolation systems as well. And on top of all of that, even if you manage to screen out all the mechanical coupling, there's unfortunately the gravitational coupling that we can't screen out because we actually want to measure gravity in the first place. So if you imagine a seismic wave, it's a pressure wave in the rock. And when the pressure is high, the rock is actually compressed slightly. And because it's compressed, it's denser than average. And because it's denser than average, it exerts a gravitational pull on the mirrors that tends to pull them along with the seismic waves. So this tiny effect, I mean, you probably never even thought about it, but it's there as a small gravitational coupling from seismic waves to the detector. And you can't really get around these things at all on the Earth. And so that's why one of the challenges that we're working on at the moment is looking at sending a detector into space, which is hopefully going to open up a whole new range of objects for us to look at.
Yeah, thanks a lot, John. That's definitely clear, and I didn't have indeed any idea of all these sources of noise, which is pretty incredible that we're able to filter that out, knowing that already the signals you're looking at are already so weak, so that it feels pretty incredible to still be able to do it, even though the signals are weak and there is a lot of noise.
It's really amazing. The technology that is required to do these experiments has been developed decades and decades for people to develop it. And almost all aspects of the detectors have to be invented for that purpose. There's very little off-the-shelf technology. And of course, the spin-offs from that then taken up in other areas, but it's the pure science that was driving the development of a lot of it.
Yeah, exactly. It's like it's not even as if all the engineering of these was already available and you could just go on Amazon and buy it, right? You have like everything has to be developed custom for these, and you don't even know if that's gonna work before you actually try it out. So that's like all these endeavors are absolutely incredible. And so that makes me think, and I think on these, Christopher, you'll have stuff to add. Because if I understood correctly, all these detectors that we have right now are on Earth, these gravitational waves detectors. Hopefully, we'll be able to do a video documentary on learn-based stats in one of these detectors. It's just some of the backstage I'm telling to the listeners. We'll see if that's possible. But so these detectors are on Earth. If you go to space and we're able to put one of these detectors around the Earth, or I don't know, in space floating somewhere, I'm guessing that solves these problems, even though there are other sources of issues if you do that in space. But if I understood correctly, the LISA mission is space-based. And so is that a way of doing that? Can you tell us a bit more about that, Christopher? And mainly tell us what the discoveries will be with that. Also, the data analysis problems that will engender, especially when it comes to the size of the data. I'm guessing.
Yeah, so LISA's space-based gravitational wave mission, it's led by the European Space Agency with NASA as a junior partner there. And the idea is we launch a constellation of satellites, so 3 satellites that will orbit around the sun, lagging behind the Earth in a triangular formation, and we bounce the lasers between them to make the same sort of measurements that we do for gravitational waves, but over a much larger scale, so really massive arms. So this is great because we can avoid the ground-based noise that John mentioned. And this is really good. So for LISA, we're not trying to see exactly the same sources as with our ground-based detectors, but we're trying to look for lower frequencies. So one of the things we've learned in astronomy over the last century or so is that each time you observe in the universe in a new way, you discover new things. So we want to look at a different part of the spectrum of gravitational waves. So LISA is most sensitive in the millihertz range, so much lower frequencies. And a much lower frequency gravitational wave corresponds to a bigger source, basically. So it's either could be the same type of binary, but just much further apart in that orbit, so much earlier before they come in and merge much further apart, or we could be looking at much more massive objects, so massive black holes. We believe at the center of every galaxy is a massive black hole. Our own galaxy has one about 4 million solar masses, 4 million times the mass of our sun. And we think galaxies merge, and so the massive black holes should merge. And so we'll be able to see these out to a much greater distance. So yeah, LISA's objective is to see what we can observe in the gravitational wave sky at these much lower frequencies. And there's a whole host of different sources. So these massive black hole mergers, we should be able to see out across the entire history of the universe. We should be able to see regular stellar mass black holes, so black holes formed from stars at the end of their lives, spiraling into these supermassive black holes. So a topic I've studied quite a lot. Those signals are extremely complicated. The orbits they undergo are very intricate, which is great if we observe one because we can measure the parameters to tiny, tiny precision, to 1 part in a million, something like that. But it's a huge pain from a data analysis point of view because you've got to find the part of parameter space where this is. And we're also going to see huge numbers of binaries in our own galaxy of white dwarfs, maybe neutron star white dwarfs, so the wide binaries here. And so the real data analysis problem for LISA will be how to fit all of this information all at once. Because with our ground-based detectors, we, at least at the moment, we basically just see, here's a signal, and then here's another signal. So you can analyze each signal in isolation. Yeah. With LISA, you cannot. You see everything all at time. Some of these, like say the supermassive black hole mergers, might be quite short comparatively, so they're localized in time, but they will still be overlapping these long-lived signals. So the in-spiraling objects or the very wide binaries will basically be there for the entire mission or a large fraction of the mission. So to analyze the data, you need to fit everything all at once. This is what we call a global fit problem. And you potentially have hundreds of thousands of sources, each with a dozen parameters or so, maybe less for the simpler sources. But you've got to do all of these all at the same time. And it potentially does matter how you do this, because things like the massive black hole binaries are extremely loud, so signal to noise ratios of thousands. So if you get that wrong by just a little percentage, the residual power in your data stream would be enough to bias your measurements of the quieter signals underneath. So this is a huge, I think possibly the most complicated data analysis problem in astronomy. And we're just starting to figure out how we're going to tackle this. So yeah, space-based detectors, I think, extremely exciting. A whole host of new sources that we can see, a new host of astrophysics that we can unlock through these observations, but also some extremely complicated data analysis challenges that need to be tackled and solved before the mission launches in the 2030s.
And what's the timeline on this mission? Are we close to launch? Where are things right now?
Yeah, so just in the last couple of months, the mission was approved by ESA. So that's looking at the designs and going, okay, we think we can build this. And now the sort of serious work on putting it together comes. And so it's be due to launch in the 2030s. Exactly when that be, I'm sure people are very confident on when it will be, but we know space-based missions are hard. So it might, maybe it's a little early to say exactly what date it will launch, but it will go up, and then there'll be a little period of commissioning, and then it will start observing. So in the late 2030s, we should hopefully get the observations from that. So current timeline, 2035 for a launch, which I guess is good news to any of your listeners who are inspired by the problems that we're talking about and think this is really cool and think that maybe they'd like to tackle these problems. There's certainly enough time to go out, get a degree, start a PhD in the field before we get the real data.
Yeah, for sure, exactly. And I mean, also historically, these kind of huge missions tend to take a bit of delay. So like you could you can start your PhD on this. I'm guessing. I mean, that's better to launch later than to launch on time but have a mission that fails, right? So
yes, we're talking €1 billion cost of these things. So you definitely don't want it to explode on the launch pad.
Exactly. Yeah, it's way better to take a few more months and do some double checks than just launch because we said we would launch on that arbitrary date.
Yeah, the space agencies do take these things very seriously. It's been fascinating seeing the things that needed to be rubber stamped to get the approval for the mission. So very good work, people, getting that done. So there are also other proposed space-based missions, some potential ones in China. There's a potential follow-up mission, I guess slightly in the future, maybe in Japan, that's been proposed for a few years. The status of these, I guess, it's difficult getting the funding for these things. So I think it's an exciting time in the field. Hopefully we'll expand the range of gravitational waves we can detect, and that'll be great.
Yeah, for sure. And I mean, that must be... So I don't know how directly involved you are on these launch, but I'm guessing that if you're still working on these when the mission launches, I'm pretty sure the day of the launch you will be like pretty nervous and excited, right? Have you already lived that actually, or would that be new to you?
So I mean, the closest analogy would have been there was a technology mission to test some of the key components of LISA called LISA Pathfinder that went up a few years ago, an extremely successful mission. And so watching that from the sidelines, my PhD was on LISA. If this mission didn't work, then there'd be no LISA mission, so all my PhD work would be in vain. But thankfully it worked very well. And worked better than was hoped for, in fact. So that was great. And I guess that's a real testament to the experimentalists. I was saying I was feeling worried because it's my PhD work, but there are really people in the field who have spent their entire careers working on this technology, multiple decades. So it's a real testament to their determination, I guess, their vision going into a field right at the beginning before anything worked to look at these things. It's also honestly quite remarkable that we've somehow managed to convince the funding agencies to fund these things for so long before there would be scientific returns. So, we're extremely grateful that they had the forethought and the patience to invest in something so long before it would give returns.
Yeah, definitely. That must be absolutely fascinating. John, anything you want to add on that?
I think Christopher's given a great overview of LISA, which indeed will be an enormous challenge. On the ground, there are also plans to take things forward into the 2030s and beyond. Currently, there are two major new detectors in the kind of scoping design stage. One is led by the Europeans, called the Einstein Telescope, and the other one is led by the US, called Cosmic Explorer. And they're taking different approaches. They're both ground-based detectors, but the challenge there is to lower the noise floor, so giving you another sort of order of magnitude improvement in the range that you can see things to, which translates to a 1,000-fold increase in the volume that you can see things to, more or less. At these kinds of distances, you do actually have to worry a little bit about the size of the universe getting in the way of these calculations. But these new experiments will require new infrastructure, so they're also going to require fairly large investments from national indeed European level investment. A lot of the data analysis challenges for those are kind of similar to the ones that we're tackling with the current generation of ground-based detectors. But the major difference is that the signals will be much longer because the low frequency end is really the target for improvement. And because of the way that the binaries chirp, I mean, I don't think I actually told you, but they sort of make this characteristic whoop type noise. Maybe you can find a sample and crop out my pale imitation. The lower in frequency you start, the longer the signal will be. And that multiplies the amount of data that you have to analyze, which with the Bayesian problem can be a bit challenging. If you're doing many millions of likelihood evaluations, you don't want each likelihood evaluation to be too expensive. And also the signal to noise ratio will be huge, at least a factor of 10 higher. So you will run into problems with our uncertainties on the nature of the sources. So the models that we have are very good theoretical models at the moment, and they're good enough for the current generation of detectors, but they will break down once our observations become good enough. They will probably show the cracks in our current theories, which I should say is probably not a fundamental crack in the theory. I think most people probably would put their money on general relativity being correct. But the problem is that there is a translation layer between general relativity and the types of template we can use it that requires approximations and shortcuts and approximate models to be created. So there's challenges with modeling bias that are quite difficult to overcome, and people are searching that as well at the moment.
Yeah, fantastic. Thanks a lot, guys. That's really fantastic to have all these overviews of the missions. And actually, I'm wondering. So, with all that work that you've been doing, all these studies that you've been talking about since we started recording, we've been able to study actually what we want to do, right? So study the astrophysics of black holes and also some tests of general relativity, as you were saying, Christopher. Can you tell us about that? And mainly, what are the current frontiers on those fronts? What are we trying to learn with the current missions?
Well, that's a big question. General relativity, I guess we really want to find somewhere where it doesn't work. For the point of view of understanding gravity, there's this tension within physics that how do you reconcile general relativity with quantum theory? And that is rather tricky, and there are a whole host of different theoretical frameworks to try and reconcile this, but we don't know for certain what the answer is. And finding some hint where general relativity breaks down would give a pointer in the right direction. And of course, finding a place where general relativity breaks down is very difficult. The place where I think it makes sense to look most is the most extreme environment. So where is gravity strongest? Where is the space-time most dynamical? Where do things change the quickest? So black hole mergers, I think, are really, and the gravitational wave signals they emit are the best place to look for that. So that's why we're looking there. And what we'd really love to find is some deviation from general relativity that we could actually be certain is a deviation from general relativity and not just a noise artifact. So I think we're pursuing a whole host of different things to look for deviations there. Mm-hmm, on the astrophysics point of view, there's just so much we don't know about the progenitors of these sources. So how do we end up with black holes and neutron stars? So stars are pretty important in astronomy. Exactly how they work is kind of complicated, so there's a lot of uncertainties in that. And I think it's really quite remarkable how rapidly the field has progressed. So back in 2015, before we made our first detection, it wasn't at all certain that we would find pairs of black holes orbiting each other and merging. We knew there would be neutron stars, but we didn't know they were black holes because we'd never seen them. I mean, they're really hard to see, other than gravitational waves. That's kind of why we built the gravitational wave detectors. But we hadn't seen any of them. So our first detection confirmed, yes, they exist, and they exist in sufficient numbers that we can actually detect them. And then the follow-up was when we measured the masses, they were about 30 times the mass of our sun. We'd never seen black holes in that mass range before. We now know, yep, there's quite a few of them, but that whether you can form black holes that big tells you something about the way that stars live, how much mass they lose through their lifetime. So that's a key uncertainty that we don't really understand about how stars evolve. So now, as we're building up statistics, really teasing out the details of the mass distribution. What is the biggest black hole that you can build? Currently, we know there are these black holes that form from stars collapsing, and we know there are these massive stars, millions of massive black holes, millions of solar masses, maybe lightest ones, hundreds of thousands, tens of thousands. But we don't know, is there a continuous distribution of black holes in between? So are there 100,000 solar mass black holes? So that's one of the key things to figure out. Is there a key thing? Where do these big, really big, massive black holes come from? And how do stars evolve? The details of all the different ways that you could end up with massive black holes that people have theorized, which ones are correct, in what ratio out there. And then I guess one additional key thing, we talked about black holes and the nature of gravity, we've talked about how you form black holes and neutron stars. But there's also what neutron stars are really made of. Neutron stars, from their name, you might suggest, okay, they're made of very neutron-rich matter. But actually what happens inside the core of a neutron star, we get a whole host of different phase changes, really quite exotic matter going on that we can't hope to replicate in the lab here on Earth. So we really don't know how this behaves. If we did, that would be really informative for understanding the dynamics of the particles that make those. So by making measurements of the neutron stars we observe, how much they stretch and squeeze, we can hopefully get some constraints on what neutron stars are made of, which would be an exciting frontier there. John?
One thing that I think we can zoom out from looking at the individual black holes and neutron stars, and still with the theme of trying to understand gravity, is on the other scale is cosmology, the very, very largest scales. How is the universe evolving over time? And hopefully, with the current generation and the next generation, we'll be able to do cosmology in a completely different way than what we have done up till now, by looking at the gravitational wave signals. So those properties of those signals, the fact that we know exactly what they look like, their amplitude, and how it decays with distance, means that they can be used as an independent probe of cosmology. Now, we've already done this with the tiny neutron star signal and with black holes that we've seen up till now. Relatively low numbers of sources, such that the constraints that we're able to put are not yet competitive with the best constraints that we can get from other techniques. But going forward, as the numbers improve, as the SNR, signal-to-noise ratio, improves, this is going to get better and better over time. And so even if we don't see anything on the scale of the individual black holes that disagrees with general relativity, it could still help us en masse to pin down what's going on with cosmology, where there are many things that we don't understand, including discrepancies in the existing constraints that we have with different methods that need a third party to come along and resolve them.
And I'm curious, so among all of these burning issues, burning questions, if you could choose one that you're sure you're going to get the answer to before you die, what would it be?
I don't know. I don't know how long I'm going to live, but the thing that really motivates me is trying to understand whether the black holes that we're seeing really are the things that you can write down with pencil and paper when you're teaching people general relativity, or are they more complicated than that in reality? I think if there was one problem I had to choose in this field, that would be the one that I found the most interesting.
I think I'd really like to know the answer to that one as well. I think that might be one of the most challenging to actually get the solution to.
In fact, the best way to answer it might be to travel into a black hole. But then the question of whether you've observe anything before you die becomes rather technical.
Yeah.
So certainly something not advised for your listeners to give that a go.
I am not sure it would end up like Matthew McConaughey in the what's the movie? You know that
It's Interstellar. So
Interstellar.
Kip Thorne is one of the founders of LIGO. He got one of the recipients of the Nobel Prize for gravitational wave detectors. He's behind Interstellar. So he advised on a lot of it. The bit at the end is not backed up by science, but
for sure.
At
least for now.
They originally were going to have the wormhole thing that opens up in Interstellar. They're going to have that detected with gravitational waves at LIGO. Unfortunately, Christopher Nolan cut that bit, so
that's a shame.
Wasn't in the film. So alas.
Well, maybe that would be for Interstellar too. We don't know. So guys, thanks a lot. I've already taken a lot of your time. And I still have like I could talk for hours because this is really, really fascinating. But it's time to call it a show. Before that, though, as usual, I'm gonna ask you the two questions I ask every guest at the end of the show. First one: if you had unlimited time and resources, which problem would you try to solve? Who wants to start?
I think if you're really serious about the unlimited time resources, then the most pressing problem, I think, would be nothing to do with gravitational waves, but is more to do with the climate breakdown. So if you want an honest answer, that's my answer, is solve climate change.
That's a very popular answer.
Yeah, get nuclear fusion working. And that would be very nice. In our field with infinite resources, tackle the quantum theory of gravity and get the evidence for that. Would be nice.
Yeah, definitely. That is a great answer. And I think also some people answered that. So you're in good company, Christopher. And second question: if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be? Maybe Christopher.
My answer for dead, I think, for this podcast, Edmund James would be my choice. You may know him if you're a Bayesian.
Yeah.
I think he would be very good dinner company. And his textbook was one of the formative influences on me as a young Bayesian.
Yeah, for sure. And there is a really great YouTube series, a playlist by Aubrey Clayton, who was here on episode 51. So Aubrey Clayton wrote a book called Bernoulli's Fallacy, The Crisis of Modern Science. Really interesting book. I'll link to the episode and also to his YouTube series where he goes through E.T. Jane's book, Probability Theory, I think it's called, which is a really great book, also really well written. And Aubrey goes through its chapters and explain the different like the ideas and so on. So that's also a very fun YouTube playlist if you.
I'm definitely going to go and look that up.
Awesome, yeah, I'll send that your way. And Christopher,
one of my favorite books. I don't know. I think I might be somewhat boring and just go for Einstein for the discussion of both gravity. I think he'd like to know what we're up to, and also just to see what his thoughts were about being such a public intellectual, and what it was like being that would be being cool. If I could invite a guest, it might be interesting to get Newton along as well. See what they think about gravity, but I think that would be quite awkward dinner conversation. I get the feeling not necessarily socially the most interactive.
Yeah. Do you think Einstein would accept at that point all the advances in all the ramifications of actually general relativity and so on, and the crazy predictions that was making, and in the end most of them, for now at least, were true, but at the end of his career he was not really accepting that. Do you think he would accept that now?
I think he would accept
yeah.
the general relativity, and he would be delighted to find that we'd seen some of the effects that he never thought would be observed. And again, he himself knew that general relativity couldn't be the final answer to the question of gravity. So he'd probably also be interested to know, have we seen any signs of it breaking down? And I think the stuff that motivated him towards the end of his career is probably still what's motivating a lot of people. So, yeah.
Well, if you are invited to such a dinner, please let me know, and I will gladly come. Awesome, guys. I think it's time to call it a show. You've been wonderful. Thanks a lot for taking so much time. As usual, I will put resources and a link to your websites in the show notes for those who want to dig deeper. The show notes are huge for this episode. I can already warn listeners. So lots of things to look at. And well, thank you again, Cruz and John, for taking the time and being on this show.
Cool. Thank you very much.
Okay,
if I may put in one thing that your listeners might like, they're interested in trying gravitational wave data analysis. Data are public. They can look up the Gravitational Wave Open Science Center, download the data there. That also, they'll find links to tutorials. There are workshops held fairly regularly that they can maybe sign up to get some data analysis experience. And there's a whole list of open source packages for gravitational wave data analysis linked from those, so they can go and tackle that themselves.
Yeah, this is indeed a very good ad. Thank you very much, Christopher. I actually already put these links in the show notes and forgot to mention them. So thank you very much, because we're all very dedicated to open science and open source here. So if any of the listeners are interested in that, like how these things are done, you have all the packages we've mentioned in the show notes, but also the open source and open science efforts from your collaborations, Christopher and John. So definitely take a look at the show notes. Everything is in there. Thank you, guys. And well, you can come back on the podcast any time, hopefully around 2034, to talk about LISA and the space-based mission.
I'll put it in my calendar. It's been a pleasure, Alex.
Perfect.
Thank you very much.
Show you had to be a good breezy and change your predictions after